everybody, and welcome to the next module of NPTEL online certification course on CMOS digital VLSI design, and we will be having this module named as Sequential Logic Design 4. So, in our previous modules we have understood what is a sequential logic and how is it different from combinational logic. We have also seen what are the limitations of sequential logic in terms of maximum operating frequency, which is not there in a combinational logic. We have understood the basic concepts of various constraints, which is basically the setup time and hold time constraints. We have also understood the basic fundamental principles of edge triggering and latch. So, difference between a register and a latch we have understood. We can have a positive edge triggered and a negative edge triggered design. We have also seen that you can have therefore sample the data in a register through your edge triggering, and you can sample your data in a latch via level triggering. So, these were the few things we have already discussed. In today's module, we will take up the further issues which are governing these sequential logic and see how we can actually modulate it or change it for obtaining the maximum usage out of the sequential logic design. As we have already understood that sequential logic is primarily acts as a memory, and therefore if even a basic memory will require a sequential logic understanding and its appreciation. So, to understand that we have already done that. So, just to give you a continuity sake, we are explaining to you what is a multiplexer-based latch. So, this is the most common edge triggered register is used. So, this is the most common edge triggered way of storing a data at a particular point of time, and then so on and so forth. So, if you see very clearly this multiplexer based latch is primarily looking like this, that you have a master, right. The concept is initially something like this. So, if you have a master, let us suppose I name it as master, and you have a slave which is like this, just name as these two modules which will be, right, and you have this is my prime input and this is my output coming out. Now, if you see the problem in the previous concept was that you required that the data should be stable till at least the setup time of the register, which means that sometimes before the rising edge of the clock your data has to be stable, right, and after the rising edge of the clock also it has to be stable for some duration of time for proper evaluation. So, that sets the limit on the frequency, right. So, what we try to do here is something like this. So, if I have an input, right, and your master is transparent to input say at some clock, so say for the rising edge of the clock, right, but latch is not transparent for the rising edge of the clock, then for the rising edge of the clock input will be sampled via the master to the output of the master. So, when the clock is rising in the rising edge of the clock, the master will actually sample the data from where? From the input. So, you have 0 1 0 1 1 so on and so forth coming here, it will sample each bit and it will store here at the slave. But since slave is actually not transparent at this stage, so this is not working at this stage, right. So, what will happen is output is basically latching on to the previous value, old value of the system, right. So, though you are sampling your data here, since your slave is not working, then you are placing the data at the input of your slave for all duration of time. During, let us suppose, the negative half cycle, or when the clock is going low, let us suppose the slave becomes transparent, but then the master becomes opaque. So, master then stops the input coming from here, and whatever data was stored here will now be sampled by slave to the output side. This is the basic concept of a mux based latch or a multiplexer based latch. You will ask me why is it done? This is done purely to negate the concept of setup time and hold time violations, right, because when your master is on and slave is off, there is no way how directly input and output are connected at any point of time, right. So, at no point of time your input and your output are connected, right, they will be always disconnected, and therefore you will always get a finite time and you can actually remove that setup time issues here, right. So just to come back to therefore to the original slide, so you term this as master. So this master is basically, let us suppose, a negative edge triggered register, and you have a slave which is basically a positive edge triggered. So as you can see here, I have given a clock here, right, and this clock, same clock is given to the slave. This is my input data bit which is coming here, right, and this path shows that it is a feedback loop available to me, and therefore any date. So what will happen is that during the negative edge of the clock, this D will be sampled to this point, but since this latch is off, right, therefore this D will be moving across this loop, and therefore this loop will be storing the value of data D for infinitely long duration of time until and unless the latch becomes the slave becomes transparent. To show that, look at the timing diagram here. So when the clock goes in the negative edge triggering of the clock, this is your data, the data is getting replicated, right, the data is getting replicated here, is it okay, at QM here, this QM is the output of the master, right, and Q is the master output of the slave. So at that point of time, Q is holding to its old data, maybe 0 or 1, whatever the data was there during the previous cycle of slave getting on, it is holding that data at this particular point, right. So in the negative edge of the clock, the D gets sampled to QM, and this D is going through an infinite feedback loop, and therefore this master is able to store the value of D at the output QM, right. This positive feedback loop helps you to store the data for a longer period of time, right. That is the reason why we do a feedback loop, because see, a data will be basically stored in form of voltages. Now if there is some leakage or something and the voltage starts to fall down, you need to again refurbish or you need to rejuvenate the voltage there. So it is always advisable to have a feedback loop, and that is the reason you are having a feedback loop in the masters. Now what is happening is, what has happened is during the rising, so we are done with this part, right. Now we go to this part, right, where you have the clock rising up, rising edge of the clock. At the rising edge of the clock, as I told to you, your data is stable here, but then your Q shows a shift depending on the value of your last value of your D stored here, fine. So I am able to have this QM here, which is this is data, the last value of your QM will be latched at this point, and therefore when the clock goes high 0 to 1, that value will be entered into this place and the Q will be stored here. So this is basically a edge triggered, a negative edge triggered master and a positive edge triggered slave configuration available to you, and this is the diagram which is quite common and used very often in these cases. Now let me show to you the mux based design using TG, using transmission gate, right. Remember, transmission gate was when basically transmission gate concept, if you remember, was that if you have an NMOS and PMOS, right, and if you have a PMOS and you have an NMOS and it is driven by say clock and this is driven by clock bar, right, then when clock is equals to 1, clock bar equals to 0, it switches on, and therefore both the devices are on, and therefore there will be flow, and there will be flow of current from input. This is your input, this is your output, and this is your input. There will be a flow of current from input to output, and the voltage will be there, and the advantage here is that you are not making the voltage fall down below a particular limit. So there is no problem of a threshold voltage drop as you see in a pass transistor logic, NMOS pass transistor logic, right. So that is the basic concept. So let us look at the basic concept here and see how it works out. So I have a TG which is T1 and T2 for the master. So this is master, this is my master configuration, right, this is my master, and this happens to be my slave, this is my slave, right. So I have a master and I have a slave available to me. This is the master which you see in front of you, and this is the slave which is in front of you. Now look very carefully, whenever your clock is, say, let us suppose the clock is high, right. Let me just let me put it in this manner, that your clock is, let us suppose, is 1, right. When the clock is 1, this is 0, this goes to 1, which means this is 1, right. So when this is 1 and this is 0, since this is NMOS, this is NMOS, right, therefore T1 is off, right, T1 is off under the condition when clock equals to 1, I suppose you understand, because when clock equals to 1, it is an inverter. So, I have a 0 here, 0 here implies that T1 will be on and this will be off, but this also implies that this 1 will directly go to this thing. So, T3 will be on, because this 0 will be coming here, right. So, T3 will be on state. So, what will happen is that T1 will be off and T3 will be on for clock 1, right. Let us look at clock 0. If I put clock equals to 0, then if this is clock equals to 0, let us suppose, then this will be equals to 1, right, and therefore T1 will be on and T3 will be off, fine. Similarly, when clock equals to 0, right, when clock equals to 0, right, similarly when the clock is equals to 0, then this 0 will be transmitted here, right, and therefore your T1 will be on, as I discussed with you. So, when clock equals to 0, T1 will be on state, right, but T2 will be still off, right. Why T2 will be off? Because your PMOS is driven by a 1 state, right. So, when T1 is on and this is when T2 is off, any data which is available here will be inverted by I1, which is a static inverter, will be fed here, and you will get here at equals to D bar, right. So, what will happen to D bar? D bar will again will through I3 it will again invert and become D here. But when it becomes D here, even so the input of your T3 will be there for D bar. So, input of your T3 will be exactly equals to D bar, but at that same instant of time, if you held your clock to be equals to 0, then you are ensuring that T3 is off. So, T3 off means your slave is basically off, it is not able to sample any data, but it is holding your previous data, and I will show you why and how. Because if you look very carefully in this case, this 0 clock 0 goes to here, and therefore your T4 is in on state. T4 is on because this is 0, this is 1, right, and therefore T4 is on. T4 on implies that this feedback loop which is available to you is always valid. So, whatever the original Q value was there is being stored in the loop of I5, T4 and I6. In this loop you are able to store the value of Q. So, what will happen if this is Q, this will go back here, you will have Q bar here, this Q bar will come here, again a Q will be coming here. So, there will be a closed loop available to you, and therefore, you will be able to restore the value here to Q. That is the reason you will have always Q here, right. But then since your T3 is off, you are not feeding any new data across this path, right. So, your slave is effectively off, it is only meant to store or rejuvenate your earlier data. Let us look at master at that point of time. So, if you have D here, which you have D bar here, so when clock equals to 0, I am assuming clock to be equals to 0, then if clock equals to 0, then as I discussed with you, T1 gets on, and therefore, this is what is happening. D bar gets to 0, it comes back to this place, here it becomes D here, right, it becomes D here. In the next phase of the clock, when clock goes to 1, this becomes 0, therefore, T2 becomes on. When T2 becomes on, D again crosses this point and reaches this point, but by that time T1 has actually become off, right. T1 has actually become 1 when clock equals to 1. So, see, let us look at quite an interesting issue here, that under the condition, it is a bit complicated to understand in the initial phase, but we will see how it, as we move along, how it works out. If you look very carefully, therefore, if I want to just break it into two parts, I have a master condition which is I1, I2, T1, T2, I3, and you have a slave which is I4, I5, I6 and T3 and T4. So, I have got two master and slave available to me here, this is your master and this is your slave. What was the concept? That if my master is on, slave will be off, and if my master is off, slave is on. So, vice versa will be there. Let us look at the fact when clock equals to 0. So, or let us look at the fact when clock equals to 0. When clock equals to 0, this is 1, T3, T1 is on. So, T1 is on, right, T1 is on. 0 means T3 is off, T3 is off, right, and your T4 is on, right, T4 is on. Why? Because this 1 will go here and it will be feeding here, and T4 will be on, and therefore T4 will be on. So, T4 will be on under the case clock equals to 0. When T4 equals to on and T3 equals to off means any data coming from QM will not be sampled by T3, and therefore T3 is in a cutoff situation, and as a result what will happen is whatever data is at Q will be reinforced here and the Q will have its original value. So, this is what we have understood when clock equals to 0. When clock equals to 1, right, and what happens to this place what happens is that when clock equals to 0, then T1 is on and T2 is off. So, when T1 is on, D goes to D bar here and D bar comes to D here, but it cannot go to this path because my T3 is in off state, therefore, it goes via this path to I2 and it is stored here, right, it is stored at this particular point. But understand T2 is in the off state because you are driving it by 1. Now, when clock goes to again it goes to 0 here, again so it goes to 0 to 1 here, let us suppose. As it goes to 0 to 1, this clock goes to 1, this goes to 0. When this goes to 0, you are ensuring that this 1 actually comes here, this 0. So, 1, so when you are feeding 1, sorry, you get 0 here. When you put 0 here, then you are switching off T1. So, when clock equals to 1, T1 is off state, right, T1 is off state, but what happens to T2? T2 is in on state, and similarly what happens to T3? T3 is also in the on state, but what happens to T4? T4 is in the off state. So, what has happened is I have disconnected this feedback loop. Now, any data available at this point will be accepted by T3 and it will be stored somewhere here, fine. You got the whole idea that what is basically the conceptual concept of this master slave latch, that master slave negative and positive edge triggered design, mux based design, that you are at one point of time storing a data and removing a data and so on and so forth. So, if we look very carefully and we have a look into it, then your this is the propagation delay for inverter, each inverter, right. Why there are 3 inverters? Because if you look very carefully, it is I1, it comes here I3 and I2. So, there are 3 inverters I1, I2 and I3, right. If you multiply with 3 times, you get the total delay out of these 3 plots plus the transmission gate delay of T2. What does it mean? That your setup time should be at least equal to this much, and the reason being very simple, that you have to wait till a data at D is being processed by all these stuff, means sorry. So, you this 3, so you will have what, I1 plus I3 plus I2 delay. So, if assuming that all of the delay are equal, so it will be 3 times the delay of individual cell, right. So, PD inverter plus delay of T3. So, T3 will have certain delay available to it. So, T1, sorry, T1. So, delay of T1, is it okay? So, the delay of T1 plus the delay, so the data will come through I1, T1 and then goes to T3, then goes to through I2 and is stored here, which means that your next data which is coming at point D has to wait till this much amount of minimum time. Otherwise, if it comes within that same period of time, it will not be able to distinguish between the old data and the new data, right. So, that is the reason I write T setup is equal to this much, whereas we write TC to Q delay to be equals to TPD inverter plus TPD dx. Why TPD inverter? Because if you see very closely, I just have to wait till I3 and QM for the data to actually go to this much point. So, which means that when the data is actually sampled till QM, you only have to wait till the delay between these 2 points for this data to get appreciated, and therefore TC to Q, mean input to output, basic output delay to be equals to TPD inverter plus TPD. So, I4 plus I3 delay which is available to you. Now, we need to understand why T hold is equals to 0, right. That is quite interesting, why T hold is 0. T hold basically is 0, the reason being, you remember what was the hold time? Hold time was the time which the data has to be stable after the rising edge of the clock in a positive edge trigger design, right. After the positive edge trigger of the clock, this is the minimum time you have to hold so that your data is suitably sampled in the output side. Now, in this case it is 0 because at no point of time you are trying to make the input output transparent. So, there is always a logic which will differentiate between input and output, you are getting my point. So, they will be off limit to each other, they will not be equal. Instantaneously any data available at QM instantaneously can be fed to Q without violating my hold time, and therefore my T hold is equals to 0, and this is where I gain in a muxed based design, right. So, in a mux based design, my T setup is basically 3 times inverter delay plus 1 transmission gate delay, and T hold time is approximately equals to 0, because the reason being hold time is 0 because once you have evaluated your data, right, once you have evaluated your data at QM, you just have to wait for the next rising edge of the clock for the slave to sample the data. So, that is the only delay which you get, not the whole time delay available to you, right. So, that is the reason we get such type of delay, this thing is there. However, there is a problem here. See, the problem is something like this. The problem is that if you look very carefully, the clock is actually feeding 1, 2, 3, 4, 5, 6, 7, 8. So, the clock is feeding 8 transistors, right, and therefore, the clock load is typically very high, which means that the clock has to drive 8 transistors at each point of time. But please understand, this is just a single master slave configuration. So, you can have n number of such configurations. So, that n into 8 will be the total number of transistors which the clock has to drive, right, which is quite large a quantity if you appreciate very carefully, which means that the clock load becomes very high for such a configuration, because you are actually using a TG configuration there, and therefore, the capacitance is also very high, because you are driving larger number of gates. Each gate will automatically have a Cox, which is basically oxide capacitance per unit area, and therefore, if you multiply with 8 number of gates, the capacitive loading on the clock will be typically very high, right, and therefore, there might be a problem as such in terms of doing it. One way of one more thing which I should which I should keep you in mind is that this logic which you see in front of you is basically a non-ratioed logic, which means that it does not matter at this stage what should be the aspect ratio of T1, T2, T3 and T4, as long as they are able to pull the data or transmit the data from input to output. Similarly, for inverters, as long as they are able to invert the signal from 0 to 1, at this stage we are not very much interested into knowing the whole concept here, right, about time, about delay and everything else, just we are checking the functionality. So, I can afford to have a non-ratioed logic here. What people gave an idea was that let us make it ratioed, right, let us make it ratioed, and let us do one thing, that let us make the feedback loop I2 and I4. So, if you look very carefully, this is D. So, when clock, let us suppose clock equals to 0. So, clock bar will be equals to 1, which means that T1 will be in on state. As a result, D will be available here, it will be D bar here. But what about T2? Since clock bar equals to 1 and clock equals to 0, T2 will be in off state. So, when this is off, this is gone, this is not coming into picture, this D will become to D bar will take a turn here and will convert into again D here, and therefore, there will be an infinite loop available to you, right. Now, what you do in the next clock cycle, when clock equals to 1 and clock bar equals to 0, just the reverse happen, the T1 goes off and T2 goes on, fine, and therefore, whatever the value available here of the D will be sampled through T2 onto I3 I4 pair, and that will come out as Q. So, Q was again therefore not transparent to D at any point of time. So, Q and D are still non-transparent, right, and they are therefore different. But interesting idea is that if you can keep the feedback loop I2 and I4 slightly weaker transistor as compared to I1 and I3, right. Suppose you are doing I1 and I3, right, and I1 and I3 are stronger as compared to I2 and I4, which means that your forward transistors or forward inverter is stronger than your backward inverter. Then when you are actually sampling the data in the evaluation mode, which means that when your T2 is on state, then you can force the data which is here to come at this point. Whereas, if your I2 would have been very large transistor, then and if this would have been I2 would have been heavier or as would be loader than T2, then the data will not at all be read by T2. So, I2 will drag all the data, all the voltage across itself, and then you can actually there will be a feedback loop available to you, fine. So, this is the basic idea or a basic concept of a transmission gate register, right. This is a TG based register. Here you are giving it, so the clock load there was 8, here it is 4. So, you have reduced the clock load by approximately half. So in the previous case the clock load was 8, in this case the clock load is approximately equals to half, and we have achieved it by making it ratioed and making my I2 and I4 relatively less stronger as compared to I1 and I2, right. As I discussed with you, that therefore it becomes important that the cost you pay for it is basically the sizing of the transmission gate is a crucial parameter, right. And that is the major problem which you face, that you need to therefore size your transmission gate and your feedback reverse bias loop such a manner that your output is stronger as compared to the feedback loop. Another big issue which comes into picture is what is known as the reverse conduction. Now reverse conduction is something like this, that let us suppose so let us suppose my clock was equals to 0. So clock equals to 0, clock bar equals to 1, right, and clock bar equals to, so what I am trying to say is, if at all it might happen that you do have a clock overlap, which means that this ideally this is PMOS and this is your NMOS. So if we go back to the previous logic, so what I am trying to tell you is that let us suppose this is clock, right. So if this is VDD, this will also VDD, this will be 0, this will be 0, that is what is shown in the next slide, that is VDD 0 0, right. If this is what is happening, then T2 will be on, right. So T3 will be off for sure, but T2 will be on. When T2 is on, there might be a reversal from Q side towards this whole thing. So Q is the output, right, but the Q, so if you haven't made I4 less stronger as compared to I3, chances are that Q via I4 go to T2 and from T2 it goes via to this loop, and therefore it what is known as a conduction is known as reverse conduction. So you want the data to flow in the output, but in certain conditions if it is a ratioed logic, chances are that the output Q might end up somewhere in the I1 to I2 loop. As a result, when you are sampling the next set of data, the T2 transmission gate will not be able to understand which data to sample in reality. So that is a major problem of reverse conduction as far as this structure is concerned, right, and that is a major problem area of this whole design. Now so far we have all assumed that your clocks are ideal and there is a perfect inversion of clock, which means that if a clock is high, the clock bar is low and so on and so forth, right, and we have also seen that this is almost true for all the cases. But let us look at this from point of view of actual silicon. When you run the clock across a silicon, right, there are C, L, so on and so forth, as a result the clock pulse actually shift in time domain, which means that in time domain they start shifting to the right, because of delay and so on and so forth. So it might happen, see really clock and clock bar should be opposite each other, but it might happen in certain cases that clock and clock bar they are all overlapping with each other. So this is the condition of overlap. This is the condition for overlap. This is known as a 1-1 overlap, right. So similarly this is a 1-1 overlap which you see, right. So this will be basically a 1-1 overlap and therefore this is also known as clock skew for sure, but this will be basically a 1-1 overlap which you see in front of you. You ask me what is the problem? The problem is very simple and straightforward. If there is a 1-1 overlap for example, then let us see what happens, what is the problem which you will face. So the problem which you will face is that if it is a 1-1 overlap, which means that your 1-1 overlap basically means clock equals to 1 and let us suppose clock bar is also equals to 1, right. If both are 1, then let me go back to the previous slide again, and if you see, then if both clock and clock bar are equal to 1, then this will be 1, right, and clock will be also equals to 1, this will be also 1, this will be also 1, right. If these two are 1 here, right, and this is 1, this is 1 and this is 1, then there might be a chance that the NMOS of T2 and of T1 they might get switched on at the same instant of time, and therefore you might have a chance that you will have a reverse conduction up till point D, right, and that is a major problem area when you discuss about non-ideal clock signals, right. similarly, if you look at this slide which is in front of you, if clock equals to 0, say clock equals to 1, then clock bar equals to 0. If clock bar equals to 0, clock 1 will make D equals to A, and A will come here, X will be equals to A bar, X will be equals to A bar, and B will be equals to A. So, when clock bar is exactly equals to 1 also because of 1 to 1 overlap, this A will be fed here and you will again get the same A bar and A, right. So, even in the condition of overlap, this will still behave like a simple master condition, right. So, we will stop here now and we will discuss the next in the next 20 minutes. Thank you very much.